For our third part of Notes 13, we're going to expand on what we've seen with our cane toad example. In that case, we looked at 60 different random samples from our population. And then we also looked at many more, like 1,000 random samples from our population. And we were able to see that some patterns and things like that start to emerge. But usually we don't have the luxury of being able to take 60 or 1,000 different random samples. Usually we only have one random sample. And so what we want to do is use statistical theory, use these patterns that other people have already discovered to help us answer questions in cases where we really do only have that one random sample. And we did something like this before with the age discrimination example. That was what helped lead us into this idea of sampling distributions earlier in the semester. And so we're going to do something very similar here with this idea of studying proportions. So we've got a new test statistic that we can calculate. And remember that a test statistic is a summary of our sample in relation to our null model. So previously, all of our test statistics were calculated as t equals some number. This is our first one that we're going to call z instead. And the reason that we called all of the other ones t was because they followed a t-distribution. So if we took a whole bunch of random samples and calculated those numbers, they would look like a t-distribution. Now in this case, if we take a whole bunch of random samples and we calculate this number, they'll start to look like what we call a standard normal or a z-distribution. And this is a normal distribution with a mean of 0 and a standard deviation of 1. So it looks like a bell-shaped curve, just like the t-distribution does, but they'll fall into this specific version of that picture. And the way that we calculate our test statistic, the part that's based on our sample, is we take our sample proportion, and then just like before, where we would have subtracted mu, and we got that mu from our null hypothesis, we're going to subtract off p, which is our population proportion, and we're going to use what we think p is from our null hypothesis. So sample proportion minus what our null hypothesis says the population proportion is. And then you'll see p show up here and here in this 1 minus p. And then we'll divide by our sample size here on the bottom. All right, and we'll take the square root of this part. And so this is our new test statistic that when we're doing a problem about proportions, so when we have qualitative or categorical data, this is the number that we're going to calculate to try and do like a hypothesis test. And so we might look at how can we use this standard normal distribution to get, say, a p-value. And you're going to see that it's very similar to what we did before. We can still use StatKey. We're going to select normal instead of t. We're still going to choose left, right, or two-tail based on whatever symbol we see in our alternative hypothesis. And then we're also going to change the number along the bottom to our test statistic. And what you'll notice is that I've basically skipped a step from when we worked with the t-distribution because the normal distribution doesn't have degrees of freedom like the t-distribution does. So we can look at an example of this real quick. Let's say I want to know the probability or how likely it is that I would get a z test statistic less than 1.96. So I'll go to StatKey and I will click on normal, and you can see that it didn't ask me for degrees of freedom. And I said I want to know how likely it is to get less than something, so I'll click left tail, and specifically less than 1.96, so I'm changing this number on the bottom, and you can see that that probability is 0.975. So pretty similar to what we've done before. And there's a couple other examples in the notes right below this. Let's say I wanted the probability that z is greater than 1.75. You can see that I chose right tail instead of left tail, and that I changed this number to 1.75, and I got 0.04 there. If I wanted the probability z is less than negative 2.8, I'll choose left tail because I said less than. I'll change this to negative 2.8, and you can see that that shaded area is 0.0026. So we'll do some more examples of this coming up, but this is basically how we would find a p-value if we had our test statistic already. And so we might want to look at what are possible hypotheses that we might do when we're doing a hypothesis test related to a population proportion. And just like we saw with population means, there's sort of three different pairs that we might set up. In each case, our null hypothesis is going to say that the population proportion equals some number. So recall that before we would have said like the population mean equals a number. Now we're talking about proportions, so we replace mu with the letter p to represent that population proportion. And then we've got three options. Our alternative hypothesis could say that p is not that number, it could say that p is less than that number, or it could say that p is greater than that number. And again, just like we saw in problems related to means, we would use the same number for our null and alternative hypotheses, but in this case, the number we choose should be between 0 and 1, because proportions are numbers between 0 and 1. All right, so if we look at that test statistic again, I want you to bring you back to this idea that we introduced previously about how most of the test statistics we'll see this semester all follow a very similar format. In each case, the top of our test statistic is some sort of estimate of the thing that we want to know, minus our theory from our null hypothesis, and then we divide by what we're calling the standard error of our estimate, and that's really just a way of saying how much will our estimates vary from sample to sample just due to sort of random chance. So in this case, we want to know the population proportion. P hat is our best guess for that value. We would plug in whatever our null hypothesis thinks p is, and then this would tell us how much our p hat values would vary from sample to sample. So usually we calculate a test statistic. We then want to find a p-value, but that p-value relies on the sampling distribution. And we can only use these sampling distributions if certain conditions are true. So we need to make certain assumptions about the population to be able to answer questions. And again, we saw this in our previous ones, but when we're talking about proportions or using qualitative data, we've got certain different assumptions from the ones that we've seen before. So just like before, we need our data to be a random sample. The whole point of most of the statistical tests that we're doing is that we have this sort of snapshot of our population, and it sort of represents our population well. And if our data is not a random sample, we can't feel comfortable that that's the case. So you would read the setup to the problem or ask whoever collected the data to assess whether the data is a random sample. Our other two assumptions, they almost seem like they contradict each other or seem like they wouldn't really go together, but I'll explain why both of these are important. So the first thing we need is that our sample is big enough. And what I mean by that, or the reason behind it, is that we said that our sampling distribution, if we took a whole bunch of random samples and calculated this number, would be a normal or bell-shaped distribution. Now, if our sample size is pretty small, let's say 4, there's only so many different things that could happen when you're talking about proportions. Because I can either have, 0, 1, 2, 3, or 4 of the people in my sample that have whatever condition I'm talking about. And so there's really only a small number of possible test statistics that I could get as well. And that's not going to look like a normal distribution. It's going to look really sort of jagged. So what we've decided is that as long as our sample size times our sample proportion times 1 minus our sample proportion is at least 10, we're going to consider that a big enough sample for our test statistics to actually have this sampling distribution that we want. If your sample size is too small, this won't be true, and then things might not work out the way that we want them to. So we need to make sure that we've seen enough of the population to really have at least a little bit of an understanding of what's going on in it. The third condition sounds a little bit weird. We don't want our sample to be too much of the population. And it sounds a little bit weird because we're used to this idea that the more data you have, the better. And that's actually still the case. If I had a sample of 1,000 people and I had information from 999 of them, that would be awesome. I would do a really good job of telling you what that population looked like. But in that case, I wouldn't need to use these methods. This wouldn't be the right way to answer that question. And so that's basically what's going on here, is if my sample is too much of my population, say 999 out of 1,000 people, then I shouldn't just do this. I'm going to get slightly misleading answers if I do. So what we're going to do is we're going to take our sample size, and we're going to say that it should be less than 1/20th of the population. If it's more than that, that's actually great. You would want to use different methods that are not the ones that we're learning right now. All right, so these are our 3 assumptions. We've got conditions for how to check them. And if these things are all true, then when we calculate a test statistic from a whole bunch of different random samples, those test statistics will fall into that normal distribution pattern, and these methods that we're going to talk about will work wonderfully. All right? We're going to pick up for the next set of notes, talking more about p-values and about how we would actually complete the rest of a problem like this once we've checked these assumptions.